Okay, now the proof is, it's nice, but it's, you know, we've come a little bit towards it already in some of the results we've proved about the Legendre symbol. But the proof is interesting. I'm following the approach taken by the book by Apostle, Introduction to Analytic Number Theory. And this presents a kind of what's called a lattice point counting technique. So you can see on one of the very last pages of the notes there's this picture of a lattice. The lattice in the plane, the integer lattice in the plane, is just simply the set of all points in the plane with integer coordinates. So it's a little bit mysterious about why, when we're talking about number theory and prime numbers and quadratic residues, why are we suddenly linking it to a kind of geometrical idea of all these kind of lattice points in the plane, and it's to do with counting these points. So how we get to that kind of geometric idea is interesting in itself. And that's what I hope to explain today, because the final proof there on the last page of the notes is it's a very straightforward counting argument, but it builds on a lot of little results that we've put together about quadratic reciprocity so far. So just a reminder, I mean, I've started all my recent lectures like this, just reminding you of where we've come to so far. But when we're talking about quadratic residues, we're framing all our results as results about the Legendre symbol, right? So this is the indicator, little indicator function. It's +1 when n is a quadratic residue mod p, and -1 when n is not a quadratic residue modulo p, or it's a non-residue. Okay, remember, being a residue means you're a square modulo p. It means you have a square root modulo p. And this is -1 if it's not. Okay, so we frame these results about quadratic residues as results about this Legendre symbol. Okay, and then a key result which got us started on all this, and which is the kind of foundation result that gets you to our proof of quadratic reciprocity, is that this result called Euler's criterion. And this said simply that the Legendre symbol NP, remember it's going to be +1 or -1, and it's congruent modulo p to this power of n. So whatever number you feed in there, n, as long as n is coprime to p, then when you raise it to the power of p -1 over 2, you either get + or -1 modulo p. Okay? And the proof of this itself, this came from our earlier work on polynomial congruences. So that was important to establishing that. Okay, I want to make this review kind of quick. I don't want to go back over everything again. Yeah. Then a later result. Okay, but this is still a kind of expensive operation to perform. You have to do p -1 over 2 multiplications. An alternative view on it was given by, come forward a bit, this result which we're saying due to Gauss here. And this allows you to calculate the Legendre symbol, so working out whether n is a square or not modulo p, by determining this number m and raising -1 to the power m. Now, remind you what was this number m. This number m, we considered all the multiples of n from 1 to p -1 over 2. Now, in the proof method, we got to this result by multiplying them all together. Of course, when you multiply those all together, you see there's p -1 over 2 copies of n there. So when you multiply them all together, you get this power n to the power p -1 over 2 that occurs in Euler's criterion. So that's how you obtain something to do with the Legendre symbol. Anyway, what this integer m is, remember, is it's a count of the number of these numbers that produce a reduced residue modulo p, so the small remainder left after division by p, which is greater than the halfway point, greater than p over 2. Okay? Some of these numbers will be congruent to a small remainder modulo p, small meaning in the first half of the residues, less than p over 2. Some of them will be congruent to a larger remainder, the ones past the halfway. And it's simply a count of the number of those which produce a residue past the halfway point. That's this number m. And you raise minus 1 to the power m. Now, of course, if you're raising minus 1 to the power m, you don't really need to know exactly what m is. You just need to know whether it's odd or even. If you know whether m is odd or even, then you know what this power minus 1 to the power m is going to be. Okay? It would be plus 1 if m is even, minus 1 if m is odd. So our next result brings us to is theorem 8.8, which is the first one we're going to work through today. And it looks quite technical, and there's, especially when you look at the proof or the other side, there's crazy summation signs flying all over the place. So it's kind of a technical algebraic argument, but this is going to be our last building block before we can give a relatively straightforward explanation for the quadratic reciprocity result. Now here, we can give a little bit of an explanation for how it is this is going to have anything to do with counting lattice points in the plane. How is it at all going to link to the idea of anything geometrical? Well, this was Euler's criterion. This was our result due to Gauss, so counting the number of these things that produced a residue past the halfway stage. We considered these multiples of n because when you multiply them all together, you get this power n to the p minus 1 over 2, which is in the Euler's criterion. But now, if you're looking at residues of these things, so an idea involved here was that we were looking at residues modulo p of a multiple jn, where j is between 1 and p minus 1 over 2. Now, when you're looking at residues modulo p of that number, what you're looking at is remainders that are left after dividing j times n by p. And you're looking at all these numbers as j goes from 1 to p minus 1 over 2. These quantities link to the geometrical idea that it's stuff to do with, something very informal, stuff to do with the line of slope n over p. Okay. So there's a line through the plane of gradient n over p. And looking at these multiples, j times n over p, from 1 to p minus 1 over 2, that's looking at it. So these are your j's along here, 1, 2, 3, and so on. So we're looking at points on this line, 1 times n over p, 2 times n over p, 3 times n over p, and so on. Now I'm not saying this is anything firm or direct, but we can pick out that there's maybe some vague relationship to lines through the plane here. Okay, because looking at the remainders that are left after you divide j times n by p, well, looking at that process, j times n divided by p, that has a link to points on this line of slope n over p. Okay, so it's this relationship which emerges in our proof of the quadratic reciprocity result. Okay. Just to remind you that quadratic reciprocity, remember, refers to the result linking this Legendre symbol PQ with the Legendre symbol QP, where P and Q are both primes, P and Q odd primes. Quadratic reciprocity says these are opposites of each other. Remember, they're each of them plus or minus 1. They carry opposite signs when both P and Q are congruent to 3 mod 4. And they're just plainly equal otherwise. This is the quadratic reciprocity result. So we're going to be, to get to quadratic reciprocity, we're going to be focusing on Legendre symbols where we've got a prime in both positions. So then this vague geometric connection will be linking to lines of slope, Q over P. So lines with slope being the ratio between two primes. Okay. So that's enough setup maybe. Let's keep proceeding and find our way to the result. Any questions first about that kind of quick summary that you'd like to ask, or anything, any clarification on it? Okay. Okay. Now, a little bit of notation, first of all. See here, we're introducing two bits of notation, square brackets and curly brackets. These are the floor function and fractional part function. It's sometimes called the integer part function and the fractional part. I'll rub off some of this. So, I mean, it's up here. So for any real number x, or rational number x, we probably don't even need real numbers. Probably just need to consider this for rational numbers. But so we write the real number x like this, where this thing here is the floor of x. This is an integer. And this is the fractional part. And this always lies between greater than or equal to 0, but strictly less than 1. Okay? So it's just this simple idea that you have x on the real number line somewhere. And slightly to the left of it will be an integer, will be the last integer before the real number x. So this number is an integer. And then this extra little step that you have to add on is the fractional part of x. Okay, so it's just this bit of notation where we can talk about the last integer less than a real number, less than or equal to the real number, and then the small little extra hop you need to add on past that integer to get to the real number x itself. Okay. So this is going to have something to do with the remainder left after dividing by something. So this is going to link to the idea of reduced residues, modulo modulus. Okay. So here's this result we're going to prove. It's a result that tells us whether m is odd or even. So this m, which occurred in the results by Gauss, remember the associated result by Gauss here, which gave you the Legendre symbol as -1 to some power m. Well, you don't actually have to find out what m is. You just need to know whether it's odd or even in order to know whether that's a +1 or a -1 for the Legendre symbol. So this is a formula. It's a formula for m modulo 2. So it's telling you whether m is congruent to 0 or 1 modulo 2. And that tells you whether m is odd or even. So the even numbers are congruent to 0. The odd numbers are congruent to 1 modulo 2. Tells you what m is, and it relates it to this interesting sum here, which is the sum of the floor of j times n over p. So j times n over p, I rubbed off my line now. These are the points on this line of slope n over p. Now the floor of j times n over p, well, that relates to counting the integer points less than one of these points. Because these points on these lines won't necessarily be at integer heights. But when you look at the floor of this number, that relates to the kind of last integers before each of these numbers. Or when we start looking at this picture of the lattice points, it's a count of the number of integer lattice points underneath that point. But we'll make that issue clear when we come to it. So it essentially says m is equal to the sum of this quantity here. Now there's another weird bit in it in general, this n minus 1 times p squared minus 1 over 8. However, when the number n we're focusing on is an odd number, this term is going to go away. Because when n is odd, this factor here, n minus 1, is even, of course. So if you're considering it modulo 2, when n is odd, this bit will be 0, because you'll have a even number here. n minus 1, when n is odd, n minus 1 will be even. So this will be even times this. So this will give you 0 modulo 2. And for considering quadratic reciprocity, we will be applying this formula in the case where n is another odd prime. So we will be able to use this simpler form of the formula here. Okay, so it picks up the same idea from our previous two results, meaning that we're looking at all these multiples of n, 1 times n, 2 times n, 3 times n, 4 times n, between 1, so j times n for j between 1 and p minus 1 over 2. Okay? These are the interesting numbers, because when you multiply them all together, you get n to the power p minus 1 over 2 times the product of all the j's times that factorial thing, and that n to the power p minus 1 over 2, from Euler's criterion, gives you the Legendre sum. So we're looking at these numbers, and we're looking at the remainders that they leave when you divide them by p. We're looking at their reduced residues modulo p. Okay. Now, this is where we bring in our floor and fractional part notation. Okay. So if you look at the fraction, if you look at the rational number j times n over p, we can write it like this. Okay, just replacing x with j times n over p. Then if we take this p and in the denominator over here and multiply both sides by p, then we get this interesting expression here that j times n is equal to this integer times p plus this extra bit here, which also has to be an integer. Okay, so these are two integers. So this bit in total must be an integer. And if you look at how big this thing is, well, the fractional part is between 0 and 1. So when you multiply it by p, it'll be between 0 and p. So this is exactly, what you're looking at here is exactly the process of integer division of j times n by p. Because we have j times n is equal to some integer, this whole square bracket times p, plus the small remainder part. And the small remainder part is between 0 and p. So this equation here is showing exactly the integer division of jn by p. And so this quantity here, p times the fractional part of j times n over p, that is exactly the least positive residue, rj, associated to the number j times n. Okay? So we get this equation here, which we will record on the board so we can look back to it. That rj, remember, we're looking at j times n. That's going to be congruent to its standard representative rj modulo p, with remainder between 0. between 1 and p it's going to be, because these numbers are never congruent to 0 modulo p. But using this idea, we say this is equal to j times n minus p times the integer part of j times n over p. Okay? So we get that nice expression. Now, you'll have to remember from in the proof of Gauss's result, in the proof of this result for the Legendre symbol, n modulo p being minus 1 to the n, we reach that by looking at all these standard residues and replacing them by the standard residues 1 up to p minus 1 over 2 with a plus or minus sign in front of it as appropriate. Now remember, some of these residues are j, some of them will be congruent, some of them will be the small remainders, the ones between 0 and p over 2. So those ones occur in this set with just a positive sign. Some of them will be large remainders past the halfway point, between p over 2 and p minus 1 over 2. Those ones, we don't consider those remainders, we consider them as minus an earlier one. So in those cases, we'll have the relevant number between 1 and p minus 1 over 2, but with a minus sign in front of it. So these epsilons, you'll recall, epsilon 1, epsilon 2, epsilon 3, etc. This is a plus or minus sign accordingly that you need to attach to the number j between 1 and p minus 1 over 2 to give you something congruent to the remainder rj. So this is quite, you know, we're building up a lot of stuff here, one on top of the other. So then what we do is we add together all of these residues. Okay. Now it's a summation type formula we're trying to get for m. In the statement of the theorem. So we're going to add together all these residues. Oh, and just remember, m is the number of minus signs that are being employed here. So the count of these epsilon things, which are actually minus 1, that's this number m here, which we need to get at, which we need to isolate. Okay, and we want to, by forming this summation quantity, we want to bring out m. So we want to make the integer m emerge out of the expression so we can get a modulo 2 result, or a modulo 2 equation for m, which is what the theorem is. It says m is congruent to something in modulo 2. And we want to get it in terms of these floors of jn's over p's. Okay? And so the way we're going to get them is, because we have this expression for the remainder rj, which employs jn over p, we're going to add up all these things. So we're going to add all those up, and within that then we'll be adding up all these. Okay. But we come at it in a very clever way, and in a very careful way. So we're going to add up all these residues. Some of these residues are the small remainders between 1 and p over 2. Those are the ones for which this epsilon sign was chosen to be plus 1. Okay, and for those j, we're just adding up j. Okay. Other of these remainders were the large ones, the ones past the halfway point. Okay, so those are represented here as minus something, minus a small remainder. But to get back the actual remainder, we need to take p minus that j. Okay? So p minus that small remainder j will give you one of the larger remainders, the ones in the second half of the group of remainders. So those are exactly the ones for which that epsilon sign was chosen to be minus. Okay? We get this very interesting expression here. The sum of all the remainders rj, j goes from 1 to p minus 1 over 2, is adding up all the j's for which we have a plus sign, and separately adding up p minus j for all the j's for which we have a minus sign. Now we bring in this expression here for Rj. So Rj is replaced by Jn minus p times the integer part of Jn over p on the left-hand side. On the right-hand side, we keep that first term the same. We keep minus the sum of all these j's the same, minus the sum of all those j's. But here we notice that we're just adding up p all the time here. So you're adding up p all the time. So you're just picking up a multiple of p. Well, which multiple of p? You're picking up m times p, because m is the count of the number of j's for which that epsilon j is minus 1. Okay, so a couple of things going on there. Replacing Rj with this expression here, which brings in the integer part of Jn over p, and noticing that this summation, the second summation here, is m different terms in it. So you pick up m times p minus the sums of all these appropriate j. In the next line, we leave the right-hand side alone. The right-hand side stays the same, and we just separate out this sum a little bit. Okay. This factor n doesn't depend on j, so that can come outside the summation. Bring that n outside the summation. Similarly, this p doesn't depend on j, so this can come outside the summation as well. Okay. So we're left with n times the sum of all the j's minus p times the sum of all the integer parts of Jn over p. Okay. Now we notice that we can express the sum of all the j's as the sum of all the j's that have a plus sign plus separately the sum of all the j's that have a minus sign. Okay. Because to every j between 1 and p minus 1 over 2, there's associated this plus or minus sign. Okay. Here are the ones in this previous line with the plus sign. Here are the ones with the minus sign. So we just note that when you're adding up, if you add all these j's together, what you're getting is the sum of all the j's between 1 and p minus 1 over 2. In the previous line, crucially, the ones with a minus sign, they actually all have a minus sign. Okay. And now, to get us to the results, to get us to something which we can simplify modulo 2, we add these two equations together. Now, this has a nice effect. On the right-hand side, when you add this right-hand side to that right-hand side, these two terms cancel with each other. So you got to minus this sum, you got to plus this. So those two cancel. These two, really nicely, are the same. So when you add them, you'll get twice it, which will simplify to nothing when you reduce it modulo 2, because 2 times something is going to be 0 modulo 2. On the right-hand side, we got the sum of all the j's, and we already have n times the sum of all the j's. So we'll be able to incorporate that easily. And that's just done on the next line. Okay. So the next line, adding the two left-hand sides, we've got n plus 1 times this sum. We did have n times it. Now we've got n plus 1 times it. We've still got the minus p times all that. Yeah, that's still there. On the right-hand side, you've still got your mp. But this second summation is gone because it's been cancelled by this one, plus this sum. And this other summation here has now got a 2 in front of it because you've added it to itself. And it's this expression now which we can simplify modulo 2. You see, getting to this line has introduced our m, has brought the m to us. It's also introduced the sum of all the floors of Jn over p. Okay, so we simply take this equation, and we now take the modulo 2 of it. We just consider it modulo 2. Now, what do you have on the right-hand side? Well, on the right-hand side, you've got 2 times something, 2 times an integer. So that's congruent to 0 modulo 2. You've also got p times m. Now, what is P in all of this? We're considering these Legendre symbols. In all this discussion, P is an odd prime. Okay, it's a prime strictly greater than 2. So P is odd. Well, that means modulo 2, P is just congruent to 1. It's an odd number. So odd number times m, when you consider it modulo 2, you just get m. So the right-hand side simplifies vastly to just m modulo 2. All this right-hand side here is congruent to m modulo 2. Remember, there's only two options modulo 2, 0 or 1. Binary. What do we have on the left-hand side? Modulo 2. Well, again, this P here, we replace by 1, because P is congruent to 1 modulo 2. So we just have this summation of all these integer parts. Keep that. This summation here now, this we can actually calculate. This is just adding all the j's from j equals 1 to p minus 1 over 2. Just that nice arithmetic series. If you apply the formula, you find it's p squared minus 1 over 8. That's first year stuff. Just adding up all the j's from j equals 1 to some endpoint. It's just an arithmetic summation formula for that. Okay. That amounts to p squared minus 1 over 8. And some reason I've gone from n plus 1 to n minus 1. I think that's just to get it to agree with the formula. Of course, n plus 1 and n minus 1 are congruent to one another modulo 2, because they differ by 2. I think that's just to get it to agree with the initial formula. Equally well, you could leave it as n plus 1 as well. If it's in a modulo 2 formula, n plus 1 is the same as n minus 1. It doesn't make any difference. That's it. That's the result. So this is the formula in the statement of the theorem. It's a modulo 2 expression for m, which is all we need to know about m, because all we do with m is raise minus 1 to the power of it. So being able to evaluate this expression over here, and there's nothing too complicated in working this out. You know, given n and given p, this is just an expression involving n and p. And this is summing these integer parts. So you have to work out what j times n is, divided by p, and find the largest integer smaller than that. It's a straightforward calculation. This is all integers on the left-hand side, so you add them, you add them all up, and you know whether it's 0 or 1 modulo 2. So you know whether or not n is going to be a quadratic residue or not. The final thing to notice is, if the number n is itself a prime, as it is when we're considering quadratic reciprocity, because considering quadratic reciprocity, we consider one prime modulo another one, whether that prime is a square modulo the other one. In that case, n is again another odd prime. So this quantity here, n minus 1, is even. So that effectively rubs that out, because it's a modulo 2 formula. So even times an integer is 0 when you're considering it modulo 2. So let's put that simpler form. So we say QP is equal to minus 1 to the power m, where after this result here now, we know that m is congruent to just the sum from j equals 1 to p minus 1 over 2. And you're just adding up the floor of j times q over p. Okay? This is the form of this result which we're interested in. This is going to finally get us to this nice result about quadratic reciprocity. And to finally prove it now, or any questions at this point? Well, question at this point. I mean, I admit there is some nifty footwork going on with those summations signed up. And even just when you glance at the page, there's a lot of summations flying around. The summations are complex in that they have ranges for the index, but also logical conditions on the indexes. These summations only gathers in the j's in this interval satisfying ej is plus epsilon j is plus 1. This summation is only those j's in the interval for which epsilon j is minus 1. So there's some sophisticated notational manipulation going on there. But so it's a bit, it's not something you can take in and completely digest and completely be satisfied with first time. You know, it takes a bit of examination of it. But none of the individual steps are that hard. You know, it's just careful manipulation. But now we can make this kind of a jump over to this geometric viewpoint. Okay, from this observation that if you're looking at, so in order to determine whether this is a quadratic residue modulo that, we have to add up all these things. But these things, j times q over p, these are all points along a line of a fixed gradient, of gradient q over p. So that steps us over into a geometric viewpoint. And moreover, it brings in what's called the integer lattice, okay? So we fast forward a few pages there now. Now, the material on the following pages is introducing the notion of quadratic reciprocity. We've already lived with that for quite a few weeks. So we're stepping now to consider this picture. So this picture here is a nice version of this one here. Okay, it's the usual plane. It's got the integer lattice on it. So that is we're just focusing on the points with integer coordinates. It's also got a line through it, as you can see. And this line joins the origin to the point PQ. Yeah, so this is the line with gradient. What's its gradient? Well, it's just the y coordinate over the x coordinate. The y coordinate, the gradient of this line is q over p. First thing to be aware of is, are there any integer lattice points on this line in the picture? Yeah, there's a couple of them. The origin is on the line, because the line is going through the origin. And that point up there, the point with coordinates PQ, is on the line. But there is no other integer lattice point on that line. Now, just to confuse the heck out of you, I have put a point on the line, but that's got coordinates P over 2, Q over 2. Those are not integers. P and Q are odd primes, right? So that, see, there's a convention here. I've filled in some of the dots as heavy. So the black filled in dots are definitely lattice points. This point here, which is, look in your notes, is an open dot or an unfilled dot. That's not a lattice point. But I've just put it there because we want to refer to it slightly. Now, these multiples, j times q over p, those are the points on this line at x coordinate j as you move across the picture. So there's a direct connection between these quantities here and what's going on the line. But it isn't just jq over p, it's the floor of jq over p. The largest integer smaller than jq over p. In terms of the picture, that is the number of lattice points here underneath position, at position j. The number of lattice points underneath the line. Okay, so there's a number of connections between this expression here and this geometric picture. Now, how does the proof proceed? The proof proceeds is we set ourselves, well, first of all, we quote a little bit tight here. But to prove quadratic reciprocity will be proved. I got quadratic reciprocity gone from the board, but quadratic reciprocity is equivalent to this expression here. That the product of the two Legendre symbols, this is PQ, QP, the product of the two Legendre symbols is -1 to this interesting power. P minus 1 over 2 times Q minus 1 over 2. Now, whether or not this is plus 1 or minus 1 depends on the status of this product here, modulo 2. Okay. The only time the product P minus 1 over 2 times Q minus 1 over 2, the only time that comes out as being an odd number is when P and Q are both congruent to 3 modulo 4. Okay. When P and Q are both congruent to 3 modulo 4, then P minus 1 over 2 is odd and Q minus 1 over 2 is odd. So the product is odd, so minus 1 to odd gives you minus 1, and that shows that these two Legendre symbols have opposite sign because they multiply together to give you minus 1. In all other cases for P and Q, one or both of these will be even, so it will be minus 1 to the power even, so it'll be plus 1, and that tells you that the two Legendre symbols multiply together to give plus 1, so they're either both plus or they're both minus. They have the same sign. Now this number P minus 1 over 2 multiplied by Q minus 1 over 2, that is interesting because that is the number of lattice points shown in the diagram. Because we've got column 1, column 2, etc., up to column P minus 1 over 2. And you've got row 1, row 2, row 3, up to row Q minus 1 over 2. It's a simple rectangle. So in one sense, how many black dots are there on the screen? Obviously, the number of rows times the number of columns. It's just a rectangle of dots. Easy. Q minus 1 over 2 times P minus 1 over 2. So that's one way of counting them. The other way of counting them is to count them in the two triangles. So all the black dots, they subdivide into the dots beneath the line, which is triangle 1, and the dots above the line in the triangle area, triangle 2. Okay. So the number of black dots in the picture is the number of dots here plus the number of dots here. Okay. The number of dots here will turn out is exactly this expression here. Is exactly this expression here. Okay. The integer part. So in there it's written down with J's. Here it's written down with T's. The integer part of TQ over P is the number of lattice points underneath the line in column T. And so when you perform that summation, when you add them all up, you get capital M1, which is the number of lattice points in T1. When you look at the picture from the other side, you turn your head sideways, so the other axis is now the horizontal axis, and maybe you flip it over. So you're just doing things in reverse. When you look at it from that side, the line is a line with gradient P over Q. So we're interchanging the X and Y coordinates. So it flips around. The number of lattice points in M2 is this summation here, adding up all the floors of S times P over Q. And clearly, when we add those two together, we get the total number of lattice points that there are in the line, which we already know just by simple counting of the rectangular points, is this product, P minus 1 over 2 times Q minus 1 over 2. So the previous result tells us that each Legendre symbol is minus 1 to the power n. Okay, so applying that here, it gives us this result. But the product of both of these is minus 1 to the total number of lattice points that there are. Capital M1 plus M2. Total number of lattice points that there are, which is this product here, P minus 1 over 2 times Q minus 1 over 2. Okay? And the fact that this is equivalent to the quadratic reciprocity law that we've been stating and repeating up to now is gotten by considering whether this thing here is odd or even, and you can link that to whether P and Q, what they're congruent to in modulo 4. Okay, so that was good. We finally got through it. We finally got to the